In the previous 3 or 4 sessions, we have been discussing about the flexibility matrix method. Now, in those sections, we have learned how to develop the flexibility matrix, that is delta matrix, and the displacement vector delta L through structure or system approach directly. Now here we are going to discuss about a systematic approach through which we can develop the flexibility matrix and the displacement vector. We call that as the element approach. And before going to the element approach, we have to see what is a typical element in a beam based or a frame kind of structure, within jointed frame kind of structure, and a typical element in case of a plain truss structure. So this is a typical beam element having properties Young's modulus, second moment of area, and length. So these two are the coordinates for the beam element. Generally, when we have an element, the coordinates are usually given as 1 star, 2 star. So the star represents element property, and this is a typical plane truss element. This has only one coordinate, and the coordinate is, say, axial. It can be axial, elongation, or shortening in this truss element. The properties are area of cross section, Young's modulus, and length. Now, the flexibility matrix for this typical beam element can be written as delta star, star for the element, is equal to delta 1 would be the rotation at this end when the, say, R1 is equal to, R1 star rather is equal to unity, and R2 star is equal to 0. So that would be, when you apply a unit moment over here, the rotation here is equal to L by 3 EI, and at the same time, when you apply unit moment over here, the rotation at the other end is L by 6 EI with an opposite sign. And the second column would be obtained by applying a unit moment here. The rotation at this end is equal to minus L by 6 EI, and the rotation at this end is equal to L by 3 EI. That is the flexibility matrix for this typical beam element. For the plane truss element, delta star would be equal to, that is going to have only one component because we have only one coordinate over here. When you apply a unit force along this, the elongation is given by L divided by AE using Hooke's law. So deflection or elongation or shortening of this element is given by P into L divided by AE. When the force P is equal to 1, the deflection is equal to L divided by AE. That is the flexibility matrix for this truss element. That's fine. So given that, we can divide now the structures which you have seen earlier or other structures using typical beam elements as well as typical truss elements. If you do that, we can first of all represent R star as the forces corresponding to the element coordinates. Star is for element coordinates, star is for elements. So R star are the forces corresponding to element coordinates. These are the element coordinates for this beam element, and this is the element coordinate for the truss element. And we can say, for example, if you extend that to a two-span continuous beam, like this. The element coordinates are going to be, there are two elements, this one and the second one. These two are the element coordinates for this element. Let us define them by 1 star and 2 star. These two are the element coordinates for the second element, say 3 star and 4 star. Likewise, we can define the element coordinates for a truss structure also. So R star contains the forces corresponding to these element coordinates. These are the element coordinates. We know that for that structure, the degree of static indeterminacy is equal to 2, and if the moment here and the moment there are the unknowns, the structure coordinates are going to be, say, 1 and 2, like this. These are the structure coordinates, and these red ones are the element coordinates, right? So, if capital R represents the forces corresponding to the structure coordinates, the R star vector and the R vector can be connected by an F matrix. If you expand on that, let's say the first force R1 star can be given by F11 R1 plus F12 R2. In this example, R2 star would be F21 R1 plus F22 R2, and so on. So to find out this F matrix, which is generally called as the force transformation matrix, we can set the value of, say, R1 is equal to 1 and R2 and any other R's to be equal to 0, and we can develop the first column of this matrix F. When R1 is equal to 1, R2 is equal to 0, R1 star will be equal to F11. Here F21 will be given by R2 star when R1 is equal to 1 and R2 is equal to 0. So to develop the first column of the matrix, F matrix, we can set the value of R1 is equal to 1 and R2, R3, R4, if there are any, to 0. To develop the second column of the matrix, we can set the value of R2 is equal to 1 and the other R's to 0. So likewise, we can develop the force transformation matrix. So that is one relation. Now further, the work done by these R star forces over the corresponding displacements in the elements, and work done by the R forces over the corresponding displacements would be equal. If you go elaborating that to an equation, say the work done by the force R1 star would be half into R1 star into corresponding delta 1 star. R1 star is a force corresponding to 1 star, and delta 1 star is a rotation corresponding to 1 star, or displacement corresponding to 1 star, plus half into R2 star into delta 2 star and so on, is equal to half into R1 delta 1 plus half into R2 delta 2 plus etc. in a general case. So we can write this as R star, you can cut off this half from all the terms and write this as R star, which is a column vector transpose delta star, is equal to capital R transpose delta R. Let this be equation number 1. Let this be equation number 2. So work done by the element forces on the element displacements is equal to work done by the structure forces on the structure displacements. That is what is given by this equation. So we have obtained this relation. Now, if we transpose this equation, we are going to get R star transpose is equal to R transpose F transpose using the property of transpose of the product of two matrices. Let that be equation number 3. If you substitute this equation in equation number 2, so equation number 3 in equation number 2, we will end up with replacing R star transpose with this right hand side of this equation, R transpose F transpose delta star is equal to R transpose delta R. We can observe that R transpose is here as a first term, R transpose is here on the right hand side as a first term. So we can obtain the relation as delta R is equal to F transpose delta star. Let that be equation number 4. Now further, we can write using the flexibility matrix. We have written delta R is equal to delta matrix into capital R vector. So if we replace this by that, is equal to right hand side F transpose. We can now define a matrix like this delta star for all elements in the structure. So this capital delta star is equal to small delta star matrix multiplied by R star. This is delta R, this is delta star. This is for the elements, this is for the structure as a whole, for structure coordinates and element coordinates. Now, further we can replace this R star using equation number 1 again. So we are going to get this is equal to F transpose delta star F into capital R. If you look at this equation, we can see the left hand side we have a post multiplier of capital R, and right hand side also we have a post multiplier of capital R. If you remove that, we are going to get, say here, delta is equal to F transpose delta star into F. That is, let us say that is equation number 5. And further, we have equation number 4 given us delta R is equal to F transpose delta star. We can have a similar relation for the for delta L, which is the displacements corresponding to structure coordinates due to externally applied forces in a release structure. So let me make use of say this space for that. Delta L, following equation number 4, delta L will be equal to F transpose delta star L. But delta star L are the displacements corresponding to element coordinates due to externally applied loads in a release structure. Now this is equal to F transpose. You can write this delta L star as the element flexibility matrix, delta star, the same matrix over here, into, let us define another vector, say P star, where we can call P star as the element forces due to externally applied loads. So we have written the displacements in terms of the corresponding element forces. You can also call them as the, say, the equivalent joint loads. P star is also going to be called later as the equivalent joint loads. So essentially we have derived delta in terms of a force transformation matrix transpose element flexibility matrix for all elements in the structure into again F, and delta L equal to F transpose delta star into an equivalent joint load vector. So there is now a systematic way of developing this structure flexibility matrix and the structure load vector. Structure displacement vector. And now illustration of this will be carried out in detail in the coming lectures. And that is the end of this section.